Okay, so this is a cute paper that quantifies something that people have been talking about. We know we love solar panels. Renewable energy contribution from them is something we cannot do without. Of course, you need to deal with intermittency, with storage and so on, but that's already being dealt with. So this talks about increased terrestrial ecosystem carbon storage associated with global utility scale photovoltaic installation. So utility scale means they have to be a certain size, certain area coverage. Basically that means if you have a solar panel in your backyard, may not have such a significant effect, but when you go to utility scale, you begin to see some impact. So let's see what the story is all about. Yeah, how great it is that you're going to get renewable energy and then co-benefits in terms of increased terrestrial ecosystem carbon sequestration. Utility scale photovoltaic USPV stands out as one of the foremost renewable energy technologies crucial for achieving global climate targets owing to its low carbon footprint. While individual case studies exist, a comprehensive global analysis of the impacts of USPV deployment on land cover changes and subsequent carbon pool dynamics across diverse ecosystems remains lacking. People have talked about it, but nobody has quantified it. Here we show that the worldwide deployment of USPV plants between 2000 and 2018, so substantially long period, would increase the carbon pool of the host ecosystem by a total of 2.1 teragram carbon over their lifespans, as revealed by the ensemble mean of multiple data sets. So their lifetime is much longer than this period, so the total sequestration is going to be 2.1 teragrams of carbon. Although the carbon pool changes associated with global USPV deployment currently contribute approximately 15.9, or an average absolute carbon footprint of approximately 10.5. So there are some details on percentiles and ensemble means and so on. So 15.9% of the carbon footprint of USP plants. This share is projected to increase by around 7-fold by 2050 as we deploy more and more USPVs. This share is projected to increase, and then this will be driven primarily by decreasing photovoltaic manufacturing emissions as well. So as a life cycle kind of calculation. Solar PV cells are great, but you do have to worry about not only the emissions involved in producing them, the end of the cycle, end of life recycling and so on. Notably, optimizing land management strategies can potentially enhance carbon density in the hosting ecosystem of existing USPV plants by approximately 3 kilogram carbon per meter squared, thereby facilitating an average reduction of 4.3% in the carbon footprint of these USPV plants. Okay, so let's read some details. Land cover change after USPV deployment. I am jumping ahead and being very brief. Based on the global inventory of PV solar energy generating units proposed previously, we developed a time series data for global USPV installations constructed from 2000 to 2018, as we said, and they used remote sensing and machine learning algorithms to do this. On the basis of this data, they find that croplands, particularly growing C3 crops, emerged as the preferred site for deployment of USPV plants, with the exception of Africa, as we will see in a minute. Generally, C3 plants, C4 plants, they are photosynthetic pathways. A lot of the crops tend to be C3 crops, and there is evolutionary history of how they came about, or how one began to dominate versus the other, and so on. However, a reduced use of cropland for USPV deployment was witnessed, particularly for USPV plants constructed after 2013. This reduction in cropland use can be attributed to the geographical shift in USPV deployment focus from Europe towards Asia and North America, especially China and India, where croplands were utilized less frequently for US PV construction compared with Europe. In addition, food security considerations may also have a role in this shift, as the increased size of US PV plants necessitates expansive land areas for their construction. By contrast, since 2013, the use of grassland, dominantly C3 grassland for US PV construction, has increased by approximately 5% compared with prior years. Okay, how does it work? Sea pool alterations from land cover changes because of US PV. Then the land cover changes ensuing from the deployment of US PV plants induced alterations in the carbon pool of the hosting ecosystems. We estimated a global carbon pool change of 2.1 teragram carbon from the hosting ecosystems induced by US PV installations constructed between 2000 and 2018, with apparent individual differences among US PV plants. We'll see a figure. Spatial analysis revealed that US PV plants sited in Europe were the predominant contributors to the carbon gain, amounting to 2.1 teragram carbon. They're all come with certain uncertainty or range of uncertainties that I'm going to skip reading, and this is followed by installations in Asia. I don't know why I'm saying Asia, certainly Asia. By contrast, a loss in the carbon pool was observed for US PV plants on the other continents, particularly North America, by minus 0.6 teragram carbon. The carbon gain arose mainly from US PV plants that were sited on C3 cropland, which were subsequently converted to C3 grassland after construction, owing to the relatively large difference of carbon density between C3 croplands and C3 grasslands hosting US PV plants. So there is a shift in vegetation when you use croplands and go from crops to grasses, and that's carbon density accounts for additional or more carbon sequestration than before. Okay. By contrast, US PV plants sited on C3 grassland and C3 croplands whose grounds were managed as bare land dominated carbon loss attributed to the relatively large plant area and carbon density difference respectively. Notably, the source of carbon loss represented apparent variability at continent scale. US PV plants sited on C3 grassland resulted in the majority of carbon loss in Asia, while those located on forest area and shrublands dominated the carbon loss in Europe and North America respectively. So obviously land use management for US PV installation is a big contributor to whether there is carbon loss or carbon gain, and of course that means that food security is going to dominate. People are not going to worry about carbon sequestration when they go after solar PV at utility scale. There will be many other considerations. Energy security will dominate. So carbon sequestration then, or additional carbon, is just a co-benefit if appropriate lands are used often just because of other considerations, right? The effect of carbon pool change on carbon footprint of US PV. The carbon footprint of global US PV plants defined as the greenhouse gas emissions per unit of power generation from a life cycle perspective from the time they are produced to the end of life recycling, considering the contribution from carbon pool changes ranging from minus 76.3 to 94.0 grams of CO2 equivalent per kilowatt hour. So CO2 equivalent is of course when we consider non-CO2 greenhouse gases with global warming potential and life cycle global warming potential, essentially nothing else, with an average absolute value of 10.5 CO2 equivalent per kilowatt hour. So that's a positive. And this spanned I'm trying to read parentheses, which always screws up the flow of the sentences. Considering the contribution from carbon pool changes spanned I have to read the whole thing again. The carbon footprint of global US PV plants defined as the greenhouse gas emissions per unit of power generation from a life cycle perspective, considering the contribution from carbon pool changes. Where does the spanned from minus 7.8 to 182.7 gram CO2 equivalent per kilowatt hour, with a mean value of approximately 56.3 grams CO2 equivalent per kilowatt hour. There you go. Anyway, it's a substantial number. The impact of change in the carbon pool on the carbon footprint of US PV plants exhibited notable variability across individual plants, with a range extending from minus 112.9 to 106.0 positive and that is in percentage, and an average absolute impact of 15.9%. In particular, US PV plants in Europe and North America were more sensitive to carbon pool alterations, with an average absolute impact reaching up to 14.3% and 11.6% respectively between the two continents. Therefore, ignoring the contributions from changes in the carbon pool can result in substantial misestimates of the carbon footprint of US PV plants. Okay. So what are the implications for land management? Given that carbon pool changes exert a critical role in the carbon footprint of existing US PV plants and they are induced by land cover changes, we next conducted a scenario analysis to investigate the potential impacts of different land management strategies on the carbon pool of the hosting ecosystem and subsequently on the carbon footprint of these existing US PV plants in a life cycle sense. To do that, 4 hypothetical scenarios were designed to alter the current land management strategies of these global US PV plants, which you can read up in the methods section. The findings revealed a substantial carbon gain totaling 4.6 and 10.6 teragram carbon under S2 and S3, their scenarios, which were 5-fold and twice under the current baseline respectively. So I'm skipping the figures too much, so let me do some figures and come back to this. Okay, so here is the did I cut off the okay, so bare land, C4 grass, mosaic of tree and shrubs, C3 crop, mosaic cropland, shrubland, and you have C4 crops, mosaic herbaceous cover, sparse vegetation, C3 grass. So C3 crop, C3 grass, C4 grass, C4 crop, mosaic of natural vegetation, and forest. Those are the land use types. And then you have land cover in terms of percentages, the total 100%. So this is over time, and you can see how it has gone up and down in terms of the usage, and land cover percentage in terms of continents from Africa, Asia, Australia, European Union, North America, and South America. I won't go into details, but you can see, as we said before, the choices of land for utility scale PV installations has been very different in Europe and North America compared to Asia and Africa. Okay, that's the main point. Land cover patterns before and after US PV deployment. You can see here, oops, that is still figure 1. So those are the land use types. So you can see that land cover percentage here by years and by continents. So you have before and after patterns. So the bluish light here is C3 crop and C3 grass. That's the one we are focusing on. How going from C3 crop to C3 grass increased the carbon density and hence terrestrial ecosystem carbon. You can call it sequestration, but sequestration tends to have a time scale associated with it as to how long it has to stay before we can say it's put away. But over lifetime of the solar PV installation, we can still think of it as carbon that's been sequestered or put away from the atmosphere. Okay, so the spatial pattern of land cover type, as we saw, and spatial pattern of land cover type after US PV construction. So that's here. So we went from here before solar PV construction to after solar PV construction, and you can see the distribution of changes going from these colors to these, which are better captured in the other ones. So C is the changes of the proportion of different pre-construction land cover types occupied by US PV plants that we saw here. There are a lot of colors, so we don't want to stare at them too much, but you can go and look at the paper. D is the proportion of different pre-construction land cover types occupied by US plants by continent that we looked at here, fraction of vegetation types. And then E is changes in the proportion of different land cover types after the construction during 2000 and to 2018. That's still a transient period because the life cycle of these USPVs is not over yet. This is the proportion of the different types of construction by continent, so by time and by continent. And as we said, you can see EU looks very different than Africa and Asia and North America and South America, okay, especially Africa, okay. So here carbon pool changes induced by USPV deployment. There are negative and positive numbers, and Africa is tiny compared to these numbers, and so is South America. But you can see that there is a mix of numbers here over India and China, with mostly one negative number here but two positive numbers, and you can see these numbers I won't read, there are too many. So there are all the land classification times before construction, going from forest, savannas, shrublands, mountains, C4 grass, C4 crop, C3 grass, C3 crop, and bare land, etc. And here carbon pool change in the various land use types over time, and you can see lots of positive numbers and lots of negative numbers as well. The negative numbers are in the reddish orangish colors, going from mosaic tree and shrubland, spare vegetation, and forests. So the main message is that USPV can increase carbon in put away in terrestrial ecosystems, but you have to choose them carefully. Okay, this is the effects of carbon pool changes from footprint of USPV plants. So it is counted differently in terms of carbon pool induced footprint changes. So there is some modeling and estimation and scenarios involved that I'm not going to go into the details, but you can see there are various methods here used, and these are basically the spatial pattern of the impact here. The numbers overlaid on the map denote the absolute impact represented by ensemble median, and B is the absolute impact of carbon pool changes on the carbon footprint of USPV plants estimated utilizing different carbon density data sets. So these are the carbon density data sets, which itself tells you just how uncertain the numbers can be. This one is large and way out there, for example, compared to all the others, because when you have a global map like this, having carbon measurements is very sparse, and then you're estimating, and you can have large uncertainties or ranges. Okay, so this is the changes in absolute carbon pool impact on USPV carbon footprints. What do we expect according to their scenarios? Kind of shared socioeconomic pathway matches to CMIP 6. So by 2030 and by 2040 and 2050. Okay, so obviously this is impressive and can be a significant contributor, but obviously you have to also worry about how the land use changes are considered in these installations. Okay, you cannot just go around putting anywhere you want and expect additional carbon to go into land or vegetation. You need to choose based on these information on the impact based on the vegetation types that we looked at here. Okay, lots of negative numbers and some positive some positive numbers over the life cycle of the USPV. So it's not year by year. You have to really worry about long-term sequestration. Obviously not geological timescales like when we do geoengineering carbon sequestration. Okay, carbon pool change and carbon footprinting changes under different land management scenarios. So you are looking at their scenarios here, S1, S2, S3, S4. I'm not going to go into detail because scenarios always include some uncertainties, and then in this case they are assuming lots of other things about climate as well, and they are only focused on US PV plants under different scenarios compared with the current condition, and positive values represent an increase in the carbon footprint, while negative values denote a reduction in the carbon footprint. Okay, so obviously you want to have a reduction in the carbon footprint of the US PVs, so that's where the land use becomes very critical. Let's just read for completeness the scenarios. S1, the all cropland post-construction scenario under which the grounds of all US PV plants are managed as cropland. S2, all the grassland post-construction scenario under which all US PV plants manage their grounds as grasslands. S3 is optimal scenario under which all the US PV plants manage their grounds with land cover types optimized for the highest carbon density potential based on local environmental conditions. Obviously there is a range of environmental conditions here, going from mid latitudes dry to wet to mixed Mediterranean, and then to monsoon regimes and so on and so forth. So obviously you have to be specific to local environmental conditions. S4 is the worst case scenario under which the grounds of all the US PV plants are managed as bare land. N in the legend denotes the number of data sets used in the calculations. Okay, basically I'm not being very careful with the numbers because we are saying that US PVs have potential to at least reduce their carbon footprint over their life cycle, or offset their life cycle carbon footprint by increasing carbon density or carbon in the terrestrial ecosystems over their lifetime, if we choose the land use carefully, or if we choose the location of US PV carefully. Sensitivity to microclimate impact. If you have large enough scales, you will impact the microclimate, and there's been a paper also maybe about a decade ago arguing that if we covered Sahara with solar panels, then we will increase rainfall over Sahara. That paper kind of disappeared, but you can go find it. It was in Science, I think. Given that the existence of PV panels can alter the local albedo, affect the energy balance, and further result in microclimate changes, we carried out a sensitivity analysis to preliminarily reveal the impact of microclimate changes on our results. The sensitivity analysis comprised two components: an albedo-based analysis and a whole scene assessment. The results presented here were estimated using the observation-based data set. However, the results calculated utilizing the model-derived carbon density datasets can also be found in the supplementary figure and data availability section. For the albedo-based analysis, we found that on average the carbon pool of the hosting ecosystem after the construction would be enhanced by about 16% to 34%, primarily due to the temperature decreases induced by effective albedo increase estimated for most US PV plants. But you have to be careful how this carbon pool was computed. Did they use a dynamic vegetation? Did they use, they are obviously talking about C3, C4, etc. But go and look at the way the carbon pool changes were computed. Okay, an estimated average increase in carbon pool changes of 30% to 101% was then obtained, which subsequently led to a reduction in the carbon footprint of US PV plants spanning from approximately 4 to 12%. So they still have large carbon footprints. You only reduced it by 4 to 12%. Regarding the whole scene assessment, we found that in general lower temperatures and higher precipitation would lead to an increase in carbon pool of the hosting ecosystem after the construction, with the highest carbon gain surpassing 60%. By contrast, higher temperatures and lower precipitation would result in a carbon loss of up to approximately 40%. As a result, USPV deployment induced carbon pool changes would vary wildly, ranging from minus 141.2% to 208.1% positive under different scenarios. Correspondingly, the carbon footprints of USPV plants were projected to change by minus 26.2% to 12.7%. The results indicated that the carbon gain of the hosting ecosystem and the carbon footprint reduction of the USPV plants may be more substantial if microclimate impacts are considered. However, given the complexity of the microclimate impacts exerted by PV panels, which cannot be fully captured by the sensitivity analysis conducted in this study, it is suggested that more studies in microclimate changes in response to PV deployment should be carried out across PV plants located in diverse ecosystems and climate zones to bridge existing knowledge gap. Well, is this useful? I think it is. Even though when people are installing or implementing utility scale for solar farms, will they be worrying about such details? Well, eventually they have to, because they will be part of the nationally determined contributions, and you have to report and monitor everything. Plus, you will have to choose land carefully. So choosing land where the carbon intensity is either going to be reduced or the life cycle USPV carbon footprint is not going to be reduced at all, and you will obviously be not being very optimal. So it's useful. It'll be curious to, it'll be nice to see how people consider these details when they actually make the selections of where to install utility scale solar farms. Okay, so I know I kind of was very brief, but I just wanted to give you an idea that there are multiple considerations. Carbon pool changes, so increased carbon intensities in certain shifts, and worrying about the life cycle carbon footprint of the US PVs themselves, utility scale photovoltaic installations themselves. Okay, very useful in that sense.